This is the third segment introducing analysis of variance and discussing source tables. At the end of the last video, I asked you to spend some time filling in the rest of the source table based on the information that was presented earlier. We know that we have 4 different groups, and the first group had 4 individuals, and each of the remaining 3 groups had 3 individuals. So we need to fill in the rest of these values. And we can use that information that we have about group size to get our degrees of freedom. Then, once we have the degrees of freedom, we can find the mean squared and the F statistic. So here are our values if you've gone ahead and calculated them. If you haven't, then you might want to pause the video before you continue. So here's the values we had. Between groups, because we have 4 groups, we subtract 1 and we get 3. And remember, we had 4 in the first group, and then we had 3 in each of the other 3 groups. So 4 in the first group gives us degrees of freedom of 3 for group 1, and then for each of the remaining groups we have 2 for each one, totaling 6. So 3 and 6 is 9. And then our total is 12. If we took this between group sums of squares and divided by this 3, we would get our mean squared between, which is 153.881. If we divided the within group sums of squares that we previously calculated by 9 degrees of freedom, we get the mean squared within, which is 18.602. In order to get the F statistic, we basically just have to do one thing. We just need to divide the mean squares between by the mean squares within. So we could really just even write it by putting a division symbol in here. And we would calculate, if we took 153.881 and divided by 18.602, we would get this F statistic. So this is our computed F statistic, and that would be what we would have in step 5 of hypothesis testing. So we could make a decision about that particular statistic by looking up our value in the F table, which I will show you later, and make a decision to fail to reject or either reject the null hypothesis. But the real question is, what is this analysis of variance telling us to do? Do we reject or accept, or I would say reject or fail to reject the null hypothesis? And not only that, but what is it really telling us? What it is, an F-test is an omnibus test, which means that it tells us that somewhere among those means we do have a difference, but it doesn't specify where. It just tells us that it's worthwhile to do some follow-up tests, and for us to do those follow-up tests, we really need to control for type 1 error rates and make sure we maintain them at 0.05 or less. So if we wanted to look at this F statistic and make a decision, we know that it's 8.27 right here. And we looked up on our F table that the cutoff is 3.86. Do we reject the null hypothesis? Well, here's 3.86. And these little slash marks here indicate that it just keeps going because, again, remember this is an asymptote. It doesn't actually hit 0 on the x-axis over here. So we have 8.27. And it is in that shaded region, which means that we do indeed reject the null hypothesis and conclude that somewhere among those groups there is a statistically significant difference. So remember back in the beginning when we were talking about our assumptions, and we talked about the assumption of homogeneity of variance. So what we need to do is actually calculate the variances for each of our groups and make sure that our largest variance, okay, so largest variance is no more than twice the smallest variance. So in this case, our largest variance is 20.917 and our smallest is 13. So if we multiplied 13 by 2, we'd get 26, which we have up here. So we actually meet this assumption because 26, twice this smallest one, is greater than this 20.9. So we meet the assumption. All right, in order to make a decision here, we take the variance, the mean squared, we divide it, we get that by dividing the sums of squares by the degrees of freedom, and then we take the mean squared between and divide it by the mean squared within, and then we compare that calculated f to the critical value. If the calculated f is bigger than the critical value, we have a significant difference among those means. So here, moving on to effect size, we use a different effect size, and what we use is r squared. And that is basically the proportion of variance accounted for by the independent variable. So really what it tells us is how well the independent variable explains all of the variability among the scores. So how well does knowing what group somebody is in help us understand or help us account for the total of variability? So you can imagine that this would be on a different scale in terms of what those values might mean and how we'd interpret them. So we take that sums of squares between and we divide it by the total sums of squares, and it will give us a value that is a proportion. And here our conventions are a little bit different. Again, it's still by the same person, Jacob Cohen, and we see that the small effect size is 0.01, which is 1% of the variance accounted for. Here, a medium effect size is about 0.6, which is a 6%, and a large effect size is 14%. So these are different from what we've seen for Cohen's d. So lastly, we want to talk about, remember I said that analysis of variance is an omnibus test. And so what we need to do to figure out which of those groups are different from each other is use what are called post hoc tests, which means that they're conducted after the fact. So when you have three groups and f is significant, how do you know where those differences are? So we could say that we have differences between group 1 and 3. We could also say that we have differences, or we could test if there's a difference between group 1 and 2. And we could also test whether there's a difference between group 2 and 3. So those are three different comparisons that we can do. There's two different common ways that we could control for this. There's actually more than this, but these are the ones that we're going to talk about here. Very common way in most statistical packages to allow you to check these differences is called the Tukey honestly significant difference. And what it does is it gives you all possible pairwise comparisons. So we've got a pair of scores here, a pair of scores here, and a pair of scores here. Group 1 versus 3, 1 versus 2, and 2 versus 3, and it will tell you which ones are different. Another way that we could actually control for type 1, our type 1 error rate, is called the Bonferroni test. And in this case, essentially what we do is we take our decided upon alpha level and we divide it by the number of comparisons that we decide to make. And so it's very simple. We take our alpha level and we divide it by the number of comparisons. So, and that just gives us an adjusted critical value. So it basically just gives us that more strict critical value every time that you make a comparison of different means. And it just shifts that critical region so that it makes it harder to reject the null hypothesis by chance. So it really has to do with the number of comparisons we plan to make, and we divide that p-level by the number of comparisons. So here, if you were comparing two means, then you would just leave your Bonferroni, because that's one comparison, at 0.05. In our case where we had three different groups, then our number of comparisons now means that our Bonferroni has to be 0.017. If we had four groups, we'd make 6 comparisons. So we'd have group 1 versus 2, 1 versus 3, 1 versus 4, 2 versus 3, 2 versus 4, and 3 versus 4. So that gives us 6 different comparisons. Now we've divided that to 0.008. So you can see that these values, as we increase the number of comparisons we're making, get smaller and smaller and smaller. Next time, we will be talking about, this is for next week, two-way between groups analysis of variance. And essentially what we're going to talk about is source tables and how they're a little bit different, a little bit more complicated, but also interpreting a new effect called an interaction. Interactions are really interesting because what they do is allow us to look at two independent variables simultaneously. So we'll get to talk a little bit about what those effects look like and how we interpret them.